Stack6 SI works with our popular SI programmer software for creating programs to be stored in and executed by the drive. The SI programmer is easy to use, requiring no previous programming experience. You can quickly and easily create programs which include motion, I/O, an optional operator terminal, and the handling of special circumstances like user interrupts, drive faults, end of travel limits, or motor stalls. We're going to spend the next few minutes taking a tour of the SI programmer software. Then we'll create a simple program so you can see firsthand how it works. The first step in creating a program for your Stack6 is to configure the drive. If you were using a Stack6S or Q model, you would start with our configurator software. The SI programmer has all the necessary configuration tools built in, so the SI programmer software is all you need. That way, your program and the drive configuration always stay together, and you only need to learn one software tool. We'll need to tell the drive a few things about our motor. If we want to use an optional encoder, we'll need to enter the encoder resolution and choose the functionality we want. If something goes wrong with the drive, an alarm or a fault will occur. The alarms dialog can show a complete history of past alarms and faults and allow you to specify how to handle such occurrences. You'll need to tell the drive how many motor steps you want in a shaft revolution. In most cases, the default setting of 20,000 steps per rev is fine, but you'll see in a few minutes that special settings can sometimes be useful. All SI drives include programmable inputs and outputs. These can be used in your program in various ways, as we'll see later. Some inputs and outputs can be set for automatic functions like jogging or signaling a fault, with no further programming required. It's easier to create a successful program if you don't have to think on too many levels at once. The SI programmer can work in almost any units you like, so that you don't have to make conversions. The advanced electronic damping, anti-resonance, and waveform smoothing features of the Stack6 only perform at their best if we tell the drive which motor we're using and how much load inertia is connected to it. I have an HT23548 motor, which is one of many applied motion motors that have been optimized for use with the Stack6. All of the required parameters for the recommended motors are stored in a database, which the SI programmer will automatically read when I choose the motor from the drop-down list. My motor is mounted on a motorized table called a slider, and the slider manufacturer has provided me with the inertia that is reflected back to the motor. I'll enter that as 41 gram-centimeters squared. The motor dialog will accept load inertia in a variety of units, or as a ratio of the motor inertia, just in case you're estimating. You may, at your option, mount an encoder on the back of your motor, or you can order one pre-installed from us. An encoder allows the drive to know exactly where the motor is at any time and how fast it's going. If the motor stalls, the drive will know immediately and can take action. This feature is enabled simply by specifying the encoder resolution, the direction of counting, and by checking the box marked Stall Detection. If you want your program to branch to a line where you'll provide a sequence of instructions to recover from the stall, just check Branch on Stall and enter the appropriate line number. The Stack6 can also use the encoder to monitor the motor's lead angle, which is a direct indication of torque. This allows the Stack6 to continuously monitor the lead angle and alter a move profile before the motor runs out of torque and stalls. Of course, this feature cannot prevent the motor from stalling if the load encounters a rigid obstruction, so you can enable the Branch on Stall feature when using stall prevention. When you are first setting up a machine, you may find yourself experimenting a bit, and that can result in drive alarms and faults. If you change to a different motor model and forget to select the new model from the motor list, you'll usually get a motor resistance alarm. If you hit an end of travel limit unexpectedly, you'll get an alarm for that. There are 13 possible alarms and faults in all, and up to 8 occurrences are stored in memory. You can see this alarm history by clicking on the SI Programmer's Alarm button. You can also clear the history, which you may wish to do once you have a machine fully operational and are ready to ship it to the end customer. Because the Stack 6 is a microstepping drive, electronically synthesizing step positions in between the motor's natural 1.8 degree full steps, you have a wide selection of step angles. The default value of 20,000 steps per rev provides adequate smoothness for most applications, but certain other settings may provide useful unit conversions. For example, 36,000 steps per rev allows you to work in decimal degrees in a rotary application. 21,600 steps per rev equates to 1 arc minute per step for you scientific types. And 25,400 provides a conversion from inches to millimeters. More on that in a minute. The I/O dialog is where you'll define automatic I/O functions like the end of travel limits, jog inputs, and the fault output. For example, the end of travel inputs can be set for normally open, normally closed, or not used. You can choose whether to have the program halt if the motor unexpectedly strays out of bounds, or to branch to a program line. You'll also find the configuration for the automatic brake output in this dialog, and you can define an input condition to interrupt the program and branch. If a fault occurs, you could choose whether to handle it with a special section of your program or to simply halt the program. Now I'm going to set up the units of distance and speed. Our slider table has a 12-turn screw, which means that when the motor turns 12 revolutions, we get 1 inch of linear motion. At the default setting of 20,000 steps per rev, we have 12 revs per inch times 20,000 steps per rev equals 240,000 steps per inch. I'll enter that as the pitch and name the unit inch. Now my move dialogues will show distances in inches, speeds in inches per second, and accel-decel rate in inches per second squared. If I wanted to work in millimeters, that would also be possible, even with an English screw on my slider. If I were to set the Stack 6 for 25,400 steps per rev, then my user unit pitch would be 12 revs per inch times 25,400 steps per rev divided by 25.4 millimeters per inch. That's 12,000 steps per millimeter. Like most computer programs, an SI program consists of a sequence of steps, or lines. On each line, you can place an instruction. There are 23 different instructions to choose from, and many different options within each. Each program line appears on the right-hand side of the main window as an icon representing the instruction and a brief description of the options. A downward pointing arrow means that no instruction has yet been placed on that line. To define a line, just click on the icon. The program menu appears, showing all the possible instructions, plus buttons for inserting and deleting lines. There are several basic types of instructions. Motion instructions move the motor, including a fixed distance move, and a fixed distance move that automatically returns to where it began after a time delay. You can also instruct the motor to move to an absolute position from wherever it happens to be. If you connect a sensor to one of the drive's programmable inputs, you can move and stop when the sensor is activated. There is also a special instruction to follow a CNC hand wheel, so that a machine operator can visually position the load. The hand wheel instruction can also follow a master encoder, synchronizing the motor's position or speed with that of another device. Because all SI drives have at least 7 programmable inputs and 3 programmable outputs, several I/O instructions are available. Wait input tells your program to wait at a line until one or more inputs meets a specific condition. If input branches if an input condition is met. Set output activates one of the output terminals, allowing you to control other electronic devices. You can even connect the inputs and outputs of multiple SI drives together to create a multiple motor system. Since most programs don't simply run in a straight line, executing one instruction after the other, it's important to have instructions that control the flow of your program. The simplest of these is goto, which jumps to a specified line. We'll show an example of that in a few minutes. Sometimes it is necessary to repeat a sequence of instructions a fixed number of times. This is called a loop, and you create one in the SI programmer by surrounding the instructions you wish to repeat with a repeat and an end repeat. If you find yourself using the same sequence of instructions in several different places, you may wish to place those instructions on a subroutine and call it from various places. That makes your program more compact and easier to understand and maintain. All SI drives can use an optional operator terminal, or MMI. This MMI provides many useful functions. A single MMI instruction can allow the operator to set a move speed in units of your choice, and can even check to see that the value the operator enters is within a reasonable range. You can also fetch the distance of one or more moves, or a repeat loop count. The program can pause until the operator presses the MMI's enter key. Or you can ask a yes or no question and branch if the user chooses yes. It's sort of a human version of if input. You can also create a menu where the operator chooses by pressing a number key. Your program can branch to a different line for each menu item. The MMI can also serve the same function as the CNC hand wheel by allowing the user to move the load by pressing the arrow keys. The MMI can be used to display a program setting or loop count so that the operator can monitor the program as it operates. If you need to change the motor current or turn the motor on and off from your program, you'll use the change current instruction. For servo drives, this instruction can change servo loop parameters to accommodate changes in load. Let's create a simple program so you can see how the process works. Since our slider has a push-button switch that connects to input 2, let's create a program that will move the slider table 2 inches each time the switch is pressed. We've already chosen the motor, entered the load inertia, and set the units. Now we need to instruct the program to wait for the switch. Line 1 is always executed first, so I'll click on the Line 1 icon and choose Wait Input from the Program menu. The switch is connected to input 2, and when pressed, it closes. That's all we need for line 1. Now for the move. My table is marked, so I know that counterclockwise makes the table move away from the motor. To move the motor a fixed distance, we'll need the feed to length instruction. We'll set it for a distance of 2 inches at a speed of 1 inch per second. The direction must be counterclockwise. That was pretty simple too. We need one more thing. If we want the motor to move each time we press the button, we'll need the program to jump back to the wait input instruction after the move. On line 3, let's place a goto instruction that jumps to line 1. Now we're ready to try it out. The program we've created, along with the other drive settings, are stored on my PC, but have not yet been transferred to the drive. Clicking Download will do that. If I had wanted to transfer the contents of the drive to the SI Programmer software on my PC, I would click Upload. If you need to modify a program that is already stored in an SI drive, you'll want to connect the drive to the PC, launch the SI Programmer software, then power up the drive and click Upload. Now that I've downloaded the program to the drive, it's ready to run, starting on line 1. If I were to disconnect the drive from the PC and cycle power, the program would automatically run. But let's keep the drive connected for now. The SI Programmer software can help us test and debug our program by showing us what's going on inside the drive. When I press the Execute button, a small window will appear that lets me see the status of the inputs, outputs, and other drive functions, and provides me with controls to pause, run, restart, and even single-step the program. This is all very useful if you are trying to solve a problem with a complicated application. The instruction icons and descriptions in the main windows also light up yellow so that we know which instruction is executing. Let's try it now. Did you see the slider move? Let's run it again. This time, notice how the LED representing input 2 lights up when the switch closed. The Stack 6 and the blue servo drives allow you to monitor variables while the program runs. In this case, we were monitoring position. Watch it change from 0 to 480,000 steps as the move takes place. Now, let's look at the program window. While we're watching for the input to go low, line 1 is yellow. Line 2 is yellow while the motor is moving. The go-to on line 3 is hard to see because that instruction happens pretty fast. The same SI software works with many different Applied Motion SI drive models. In addition to the Stack 6, you can use your programs with the low-cost and compact DC-powered 7080i, 3540i, and 1240i drives. 3 inexpensive 110 to 220 volt AC-powered drives are available: the SI2035, SI3540, and SI5580. Just choose the power level you need for your motor. The features are the same. We also offer a family of DC and AC-powered blue servo drives, offering precision, smoothness, and power up to 1000 watts. We hope you have enjoyed this introduction to the SI family of flexible, easy-to-use, programmable motor drives. For more information, please visit our website at www.applied-motion.com.